Chapter 4, Part 5, Conformations of Alkanes. So, a reminder from Gen Chem, two groups bonded by a single bond can undergo rotation about that bond with respect to each other. A conformation is a temporary molecular shape that results from a rotation about a single bond. A conformer is referencing each possible structure of conformation. Conformational analysis is the analysis of the energy changes that occur as a molecule undergoes rotations about single bonds. So for example, all of the pictures below represent hexane. Now the first image shows just a linear hexane molecule the way that we usually draw it and the way that we usually see it. But if you were to rotate around this bond, causing this bond to come down, you would end up at this conformer. And if you were to rotate around this bond, bringing this bond over to this side, you'd have this conformer, and so forth. You could keep rotating until you also have this conformer, which simply has a rotation around this bond, but bringing this one up. And that seems really confusing when it's on paper. It's really hard to see on paper unless you've been doing this for a long time. So right now, if you're looking at this and you're like, what is going on? That's fine. So Newman projections are a way to take those ideas that we just looked at and put them on paper in a way that actually does make sense. So a Newman projection is taking a molecule that is in 3D and looking at it from the side, the way that the eyeball here is being shown. So remembering that each of these carbons are tetrahedral, imagine looking at the molecule from this direction. If you did that, you would see something that looks like this over here. But that image is a little complicated, so we're going to look at each carbon individually. Let's call this carbon A and this carbon B. So carbon A is represented here. If you were looking at this molecule from the side, you would see chlorine on the left, an ethyl group on the right, and hydrogen on the top. And behind it, you would see carbon B, and you would see a methyl to the left and above the chlorine, a hydrogen to the right above the ethyl group, and a hydroxyl group down directly opposite the hydrogen. Now a Newman projection just combines these two images so that what you're looking at down the middle of this bond is the actual bond between carbons A and B. So that bond is actually running perpendicular through the paper. So if you were to take your pencil and put the tip of your pencil on the dot that I made here, your pencil would be going through the bond. So this is a Newman projection. Here's another version of this type of image, also done in 3D ball and stick models, in case you need another view. I also have another video where I'm actually holding models and you can see me manipulate them so that you can picture these a little more easily. So this is a Newman projection of just a molecule of ethane. And so you just have the two carbon atoms, and all of the substitutions on it are hydrogens. So if we look at our Newman projection, all we see is hydrogen around the carbon. And this conformation, where all of the hydrogen atoms are perfectly equally spaced from each other, is called the staggered conformation. And this is actually the most preferable form of anything, is to be staggered and have large groups as far apart from each other as possible. This follows the same rules that you learned when you learned Vesper theory. Electron pairs repel each other. And remember that there's a lot of electron density on each of these atoms and in the bonds that hold them to the carbon. So they want to be far apart. So if we look at the bond angles here, the hydrogen pointing up on, let's call it carbon A, is directly opposite the one that's on the back carbon. So that bond angle is 100, or the torsional angle is 180 degrees. And the torsional angle between these two hydrogen atoms is 60 degrees, and that would be this hydrogen and this hydrogen in the picture. So the torsional angle is the angle that you're talking about when you're going across several bonds like that, whereas a bond angle is usually something like this. There's another really simple conformation called the eclipsed conformation, and this is the least stable conformation of anything. It's very high energy to force these areas of electron density, the hydrogen atom and the bond, to be directly in line with another one. So they are taking up the same space. I want to remind you that when you look at the ball and stick model, it looks like you have these little tiny balls representing hydrogen. They don't take up a lot of space, but the electron cloud is much larger than that. And so there's a lot of electron density around these, and they are all overlapping right now in the eclipsed conformation. So the conformational analysis shows us that there's a high energy cost rotating between the staggered conformation and the eclipsed conformation. And since these molecules are constantly rotating around those bonds, what we can infer is that the molecule is going to spend more time in staggered conformations than in eclipsed conformations. So remember that these molecules don't just sit there static in the staggered positions. If there is a sigma bond, there is constantly rotation around it. Right, this is entropy, this is disorder. Molecules don't just stay in a perfect zigzag chain all day. Remember that the higher energy something is, the less stable it is. So the eclipsed conformation is not only a really high energy cost going from staggered to eclipsed, but the eclipsed conformation isn't very stable, so it's not going to stay there for very long. The lower energy conformations are more stable, so it goes up, it immediately comes back down, and probably sits here down in the bottom of the hill before it goes up to another conformation. So let's look at the conformational analysis of butane. Butane has 2 more carbons and 4 more hydrogens than ethane. So here, where we previously had hydrogens, we're now filling in methyl groups. And the bond that we're looking down is between the bond between carbon 2 and carbon 3. And so with Newman projections, you actually have to be kind of specific. If you want to look at a specific bond, you have to say that. So this is the Newman projection of butane, looking down the bonds between carbon 2 and carbon 3. So the best conformation of butane is going to be this one, where everything is staggered and the methyl groups are opposite each other. So remember, if hydrogens have large electron clouds, methyls have huge electron clouds. So if we want to imagine that, we want the methyl groups to be opposite each other so that they have no chance of trying to share space. So here are several different conformations of butane. This is what's called the anti-conformer because the 2 largest groups are opposite each other. This is a subset of staggered conformations. If you rotate 60 degrees, these front groups, you end up with an eclipsed conformer where the methyls are eclipsing hydrogens. So this is going to be a high energy situation. And if you rotate another 60 degrees, you go back to a lower energy conformation, which is staggered, but the 2 large groups are next to each other now. So this is called the gauche conformer. And then you rotate another 60 degrees and you have another eclipsed conformer. This one's the worst of the eclipsed conformers because the 2 largest groups are directly eclipsing each other. So this is the highest energy conformer of all of these. rotate again, and we have another gauche conformer. So the methyl group in the last one was over here, but now it's on the other side. It's still the same conformer. And then if you rotate one more time, you are at yet another eclipsed conformer. This one would be equivalent to conformer number 2. And then if you rotated another 60 degrees, you'd be back at 1, which is our lowest energy. So you can see this on this energy diagram here. Our very, very best conformer is down here. So our baseline is here. And then every time that we go up to an eclipsed conformer, it's a high energy cost. You can come back down to the gauche staggered conformer. Notice that the gauche is still lower than the eclipsed, but it's higher energy than the anti conformer. And then it goes back up to the super eclipsed conformer, back down to a gauche, back up to the slightly better eclipsed conformer, and then finally back down to the anti-staggered conformer.